course into 90 minutes, so it's going to be kind of a whirlwind. So Chuck Lamphere is joining us from UW Center for Social Science, Computation, and Research. Is that right? And he's a pro at giving our workshops. We're really lucky to have him. And this is in response to our quantitative needs listening session that we had last spring. And one of the things that bubbled up was an interest in more R, basic and intermediate training as demand for R becomes more prominent among students. So thank you, Chuck, for joining us. And I think it's going to be, it'll be 90 minutes. And then if you have individual questions for Chuck, we have another half an hour scheduled with him.
Yeah, thank you. Yeah, I'm happy to be here. You'll actually see up here it says CSSS up here. So I'm also University of Washington Seattle's instructor at the Center for Statistics and the Social Sciences for R. This is my 4th term. I've now taught an Intro to R class, full term long class. You can actually get all of my lecture slides, lecture videos, all course content for the class I teach at UW if you want continuing stuff by clicking on one of the links right up there. All my course content for everything I do and teach is available freely online. This will also be the same way, put it that way. If you want to follow along in the slides, you can go ahead and click on presentation slides at the top of this website, which was sent out in an email. If you don't have the email for the link to it, it's just clamphere.github.io/intro-R workshop, where the spaces are underscores. There's also an R script file up there that you can kind of right-click, save to download, and open in RStudio that has all the code I'm going to use in the slides. So the way this presentation works, and I'll just click here to the presentation slides. I present straight off of my website. The way it works is that we'll have presentation slides that look more or less like a PowerPoint slide, but the difference between them and a PowerPoint slide is they actually have live R code embedded in all of them. So I don't have to go back and forth between RStudio and my slides. The code is actually embedded. It looks and runs just like it was in your computer. So if you follow along and use the code that I'm doing, as long as you do it all in order, it'll work perfectly on your machines. So we'll go ahead and get started. Okay, so the overview today, this is going to be a brisk introduction to R. I apologize if I talk quickly. If you don't understand something, feel free to stop me and ask questions, but otherwise this is my normal speaking speed when I teach because I cram a lot into a workshop or a class. So we're going to start with an R and RStudio orientation, talking about sort of briefly the differences between them, why you might want to use this over sort of alternative ways of doing data analysis. We're going to go into talking about packages a little bit, because packages are sort of where the real power in R comes from. It's from external software you can load into it. Creating and using objects, data frames, which are kind of flat files, what you normally use as like a matrix of your data. It's basically R's representation of a spreadsheet. We're going to talk about how you use those objects and how you, in particular, how you index them. Indexing is just how do I access particular elements. That is, maybe I just want one variable, maybe I just want one row, maybe I want a set of rows and a set of columns. Indexing is really important. Then we're going to go to basic analyses. Basic analyses will be basic base R graphics. I know at least a couple people were interested in doing ggplot. ggplot is what I use in my normal course that I teach, but it is a little bit too much to it to do in a workshop like this. I'm happy to answer questions about it, and I'm quite knowledgeable in it. And I would direct you to a lot of good resources for that if you're interested. Yeah, and we're also going to do some basic statistical models going from sort of like t-tests and chi-squareds to basic linear regression and ANOVA, sort of things people ask for in the spreadsheet that I saw. And then I'll talk about some resources at the end. This is also, if I take longer than I'm expecting, the order of things that will be sped up will be the things at the bottom of this list. So keep that in mind. Okay, so R and RStudio, my whirlwind introduction. Okay. So R is a statistical programming language. It's a programming language for statistical computing. This separates it from something that's a statistical package, like SPSS, SAS, Stata, Minitab, or something like that. Those are packages. They're not full-fledged programming languages. Though sometimes you can use a programming language in them, the way you can use Visual Basic inside of Excel, and things like that. So the question I often get asked from students who are new or coming into one of my classes is, well, if I already know how to use Stata, especially if I know how to use Stata well, why would I want to use R? And immediately I evangelize. I'm like, well, let me sell you on this. So the very first thing, and big for students anyway, is that R is free. This means you do not need a terminal server and you do not need a license to get it. You can always have a fully updated, fully functional copy of R and RStudio on any computer you have. It doesn't matter. It's completely free. All the software for it is free and must be free for it to be released publicly. Next, it has a tremendously large community for support and packages. If you run into some problem on what you're working on in R, if you Google it, 1,000 other people have had that exact same problem. You can go to Stack Overflow, Stack Exchange, something like that. You will find an answer to your question very, very quickly. And also, if there's something you want to do, a method, a technique, something you want to do, someone has definitely already written a package to do it in R. This is particularly the case for statistical things. R is much more advanced in statistical capabilities than Python. Python is a tremendously great language for data science and things like that, but it is and will continue to be behind R in cutting-edge statistics because R is a lingua franca of statistics. So people are always developing new packages. Some things like I do a lot of structural equation modeling and causal modeling. Those things are just underdeveloped in Python. I would imagine in the next 5 or 6 years that'll change, but for now, R is the only place I can effectively do my work. Next, R can handle, I say up here, virtually any data format because I have a call I go out to every time I have students in a new class. Every single term I ask them, find me a data format I cannot load into R, and I don't know, I'll buy you a bottle of wine or something like that. It hasn't happened, no one's managed to find it yet. Some people have tried and sent me things, and I found that packages exist to load these things in, or there's some relatively simple hack someone has found to do it. This is because the community is very large, and also because open source programmers, people who write stuff for R, abhor proprietary formats. One of my favorite stories is that Stata, when they went between, I think, version 12 and version 13, they made it so version 13 files could not be opened in Stata 12. The package enabling R users to open the Stata 13 files arrived online before the Stata 13 disks arrived at my university. They abhor proprietary formats, so I simply never need to go to another package to load it. And this also applies for things like GIS formats and things you wouldn't necessarily think of R being native platform. R is my native GIS, Geographical Information Systems platform for doing geospatial analysis. It can do just about everything, it can open everything. Next, big one for me, because I teach classes in reproducible research, R makes replication very easy. You can house your entire project in just a series of files all done in R. So when I say reproducible research, I mean something along the lines of you have a set of files that will go so far as to download all of the data, clean and process the data, run all of the models, generate the output, and generate the final article that you could send directly to somebody. I teach classes on how you do that full pipeline type thing. You can do it all in R. Much the way that I said before, these slides are actually done in R. The code is all embedded in them. These essentially are a reproducible research framework. At this point, I just use them for basically PowerPoint slides and things because it's so easy to do. Next, of course, tied to that is R is a language, so it can do everything. If you can do it in another programming language, you can do it in R. People have done things like make rudimentary games in R. I use R for video and image editing sometimes if I do it programmatically. I make all of my slides in R. I actually write all my journal articles in R too. Every single one of them is compiled and put together as like a dynamic document with all that stuff embedded. It doesn't look like it. People never know it has all this R code embedded in it, but it is, and then I share them all on my GitHub. And often I'll do presentations on how can my students do it. In my base intro to R class, by the end of it, all my students are making these dynamic documents and reports generated with embedded R code mixed with text. Their plots are in and everything, and they're beautifully formatted. They pop out as LaTeX-looking PDFs without them ever having to write any LaTeX. For people who are familiar with how horrible LaTeX is to write, I've punished myself with many years of LaTeX. Yeah, it can do everything. I love R. It's near and dear to my heart. So. Next, if you want to move to something else, if you learn R, R is actually quite similar to other programming languages you might want to get into. I became fluent in R as a primary language first, but I found it very easy to jump to doing, I now do microcontroller programming in C for some of my side projects because I do kind of surveillance-based field experiments. I can program in Python because I found Python a natural jump. Python's easier to learn to begin with than R. R is a little bit more complex language, but they're similar enough you can jump from one to the other quite quickly if you learn basic fundamental programming. This is really nice. Learning core programming stuff, just like I won't talk about today, but things like for loops and if and then statements, flow control, that stuff is universal across pretty much all programming languages. You learn to do it in R. If R dies sometime in the deep future, you can take all those skills and move them somewhere else just by learning a little bit different syntax. That is not the way it works for something like Stata, SPSS, SAS, where a lot of the things you learn by getting good at those are dead once that piece of software is dead. And those pieces of software are dying, except in a few realms, that being some businesses that have long-lived licenses and government where SAS has a stranglehold on the East Coast. It won't last forever. Okay. RStudio, in contrast to R, is a front end, or what is referred to in programming circles as an integrated development environment for R. What it does is it makes your experience with R easier than working with base R. RStudio can do a lot of things. First, it can organize your code, your output, and your plots in a nice way with sort of this nice browsable interface. It can auto-complete your code and highlight the syntax in your code. So it can do things like color code functions so you know which are functions. It won't color code objects you create so you know if it's black text, it's an object you've created or something like that. You can also alter how it highlights things so if you have some preferred way to display things. Typically, I display strings that is text in green and things like that. There's some conventions, integers in orange. And it will autocomplete your code. So you can actually use long variable and object names in RStudio because you just start typing them, hit tab, it will finish writing it out. It means you never need to have short, ugly variable names for things. The worst thing you can ever do is hate you from 2 years ago who used var1, var2, var3, var4 in your entire data set and then lost your code book. Right? It's happened to all of us, definitely happened to me. Doesn't anymore. Next. RStudio can help you view data and objects in R through like having a viewer that does a pop-up window. It has a nice help file viewer in the bottom right of the window, or you can move the stuff around to your heart's content, but by default it's in the bottom right. It just has some nice helpful things already built into it. It has an environment browser in the top right I'm going to talk about too. Next, and this is what I was talking about before, it enables easy integration of R code into documents. So RStudio is sort of built around the idea of doing those dynamic documents. They're R markdown documents or sleeve documents or similar. I'm not covering them today, but I have a lot of links on that resources page if you get interested in doing it, and I'm happy to field questions over email about them too, because I get super psyched about them. I actually really like questions and email questions, so if you do send me stuff later, I'm very happy to answer your questions. Yeah. Okay, so we're going to go ahead and get right started on it. So if you open up RStudio, so depending on your own computer, so I'm not about to give my lab instructions for how to open RStudio. But yeah, if you open up RStudio and go to File, New File, and RScript, and pop open a script file, you'll have an interface that looks probably something like, oh, did I close it? You loaded nicely from here earlier. Do it again. Okay. You're going to have something that probably looks like this. I already have the R script that I have for this class loaded up in here because I loaded up to test it earlier. So the way the interface for RStudio works is typically you're going to be writing your code into what is the editor, or the script editor in the top left up here. So the area where I have all that text in there is the script editor. If you're used to Stata, this is essentially your do file or your do file editor up there. If you want to do like a single line of code at a time, just run something quick you don't intend to ever run again, you'll run it instead in the console down here. Stata has similarly a console you can just type commands into. I usually type almost everything into the script section up there because typically if I type something once, I'm probably going to want to use it again or build on it or something like that. So pretty much everything gets written up in the script. Next, up in the top, by default, there's a tabbed thing here that has environment, history, and connections. The one you're most often going to use is the one that's environment here, the global environment. That is everything that is currently, every object currently loaded into what R calls its global environment. The global environment is anything that if you type its name into the console, that object will be called on and displayed into your console, or if you do something in your scripts, that will be called by any code that you write. We're going to have lots of examples of this in a minute. The global environment is where everything is. In Stata, the equivalent of that is something like all the variables listed in your data set. The difference between R and Stata, and this is a big one, is that R can have an arbitrarily large number of data sets loaded at the same time. R doesn't care if you have 10,000 different data sets loaded at the same time. It just doesn't care to it. It's just another type of object. You don't have to have only one data set loaded the way you kind of have to do with Stata and SPSS. You may have to open different instances to do ones at a time. It doesn't care. Load as many as you want until you run out of RAM. Like I have like 32 gigs of RAM on my computer because I load a lot of stuff when I work with big data. We have a cluster over at UW Seattle, but if I'm working on a project that has, I have 1-2 terabyte size data set, like I'm working with cell phone data, I can just load it all. It doesn't care. I can load 100 of those things because Hiyac has enough RAM. But yeah, it doesn't care. It just gets loaded into the environment. One disadvantage with R is that anything loaded into R is stored in your RAM, so you have to do some finicky things if you are working with truly large data and you don't have enough RAM. You'll have to like call out, but it's actually pretty easy to set up external applications. You can call out like a relational database, pull extracts, and do that kind of stuff. Way outside the bounds of today, but no, it's possible. Okay. Yeah, so kind of went over that. Code editor pane, there's a console, environment, history, And then, the bottom right. So the bottom right just has tabs with a bunch of different things. You can browse help files in the bottom right. You can view your plots. If you have some kind of HTML output, like sometimes you'll have plotting packages that actually put out web page style either plots or tables, they get viewed down there. RStudio as a whole is actually a really big web browser, and everything is being rendered like an HTML, so everything's just being displayed sort of as little web pages. It doesn't always look like it, but it is. Okay. And if you want to change how that layout is, preferences and pane layout will take care of that. You can move them around. Some people familiar with other software packages will want them in the same place. It's perfectly happy to let you move that stuff around. Okay. Any questions so far? It's a whirlwind. So, editing and running code. So there's a bunch of different ways you can run code in RStudio. So the first thing is, in the editor pane in the top left, you can highlight lines in the editor window and click Run at the top, or you can hit Control-Enter on a Windows machine, Command-Enter on a Mac, and that will run whatever code you highlight. Next, you could put your caret on the line. Caret is fancy programmer speak for the little blinking cursor that you move around in text. You could put your caret somewhere and hit Control-Enter. It will run any set of code that caret is in. You could put it dead in the middle of the text, it'll run the whole line. If you have code that spans like 3 lines and you have your caret at the end of it, it will start at the first one and run it all. Everything that's just one call, and we'll see how that works in a bit. The neat thing is that when you hit Control-Enter and your caret is there, it will go to the next line of code. So if you just want to run like 10, 20 lines of code quickly, you can just hit Control-Enter, Enter, 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 and it will just keep going down sequentially and run them all. It's pretty simple, it's pretty common in a lot of statistical packages, but you can just burn through all of them quickly. Next, you could just type individual lines in the console and press Enter. I put this last because you should do this the least. Most of the time you want to be saving your code and putting it up at the top. Anything typed into the console is going to be gone the next time you open R and you close R. You want to be saving things and doing it. But you can do that. That's the kind of thing I'll do just like off the top of my head. I want to be like, I want to know how many rows are in this thing before I actually do something with it. N row, 45 million. Not doing that right now. Reduce the size or something. But anything I'm actually going to keep, use, I care about is going to be up in the script editor. Okay. And if you run something in the console or if you run something on the script editor, regardless, the output to that is going to pop up in the console down below. And as we go through here, you'll be following along in the script file or something, you'll see the things that you run just pop up down there. Okay, so if you mess up while writing code, let's say you leave off, the most common is you leave off a parenthesis at the end of a line or something like that, R will sometimes show something that looks like this. You'll see like this is, interrupted slightly by the thing, but it's 11 minus 2 with a parenthesis in front of it. I don't have a parenthesis at the end of this line. I ran it. It goes to another line and there's a plus sign. That is R's way of saying, I'm pretty sure you forgot something, so you should fix that. And so if you add a closed parenthesis there, that would be enough. Hit Enter, it'll finish typing that out. Because it knows parentheses usually mean I'm going to keep doing something. But if you see a plus like that at the end of something you run, it's usually you left off some end of like operator like a parenthesis or something like that. It's just expecting more input. If you don't know why it's asking you for that, you don't see anything wrong, you can just hit escape and it will cancel out of whatever it's currently doing. You go back and check your code again. Okay. So these, by the way, as an example, when I say something like this, in the console, type 1, 2, 3, 4, 5, 6, 7, 8, 9, hit enter. You can see I have 1, 2, 3, 4, 5, 6, 7, 8, 9 in that block. These blocks of code were actually run when I compiled these slides. So this is embedded R code. So I know the code I've given you guys works because I've run it multiple times and it's running inside of these slides right now. And if you typed 1, 2, 3, 4, 5, 6, 7, 8, 9 into your console or into your script editor and hit enter, it should pop out 1,368. So I have a double hashtag and a 1 here. That's just to signify this is the output from R in these particular slides. You should see that. So R, imagine that, functions as a calculator. Okay. The 1 in that output there indicates the numeric index of the first element on that line of output. So there's only one element of output here because we just added 3 numbers together into a single number. But as we'll see in a bit, if we had done some operation that produced maybe 50 different elements and they went down to the second line, you'd have a number like maybe 27 would be in those brackets in the second line. That would say that the first element on that line is the 27th element of your output. It's just a simple index that lets you know when you put out a whole bunch of stuff into the console, I know that if that particular missing data that shouldn't be there, I can be like, that says 57, 58, 59, 60. It's the 60th element. I can look in my data. It's just a little helper. Okay, so in your blank R document, up in the editor, I'd like you to type, if you're following along, feel free not to, you could type SQRT 400 and click either Run or Control Enter or Command Enter. What you should get is the square root of 400, which is 20. Okay? So, what is that? SQRT, square root, is an example of a function in R. R is a functional programming language. It's built around giving things to functions that produce some sort of useful output. Okay? If we didn't have any idea what SQRT did and we wanted to know, we could do question mark SQRT. Notice no parentheses there. We're not going to give it any arguments. Question mark SQRT in the console, and it's going to open a help panel in the bottom right of RStudio. That help is going to give you probably more information than you want, especially if you're very new to R. It's going to give you a lot of it, but it gives you all of the instructions necessary once you have like a foundation in R to know how you can use any given function, all the arguments it gives, the values it puts out, and often it'll have if it's a statistical method, it'll have citations to papers at the bottom being like, this is the paper that describes where this method came from, and it'll have examples and sometimes even like references to data sets and additional things at the bottom. These help files can be very, very long and very detailed. They can also sometimes be arcane and borderline useless. So if you go into a help file and you're like, oh, that's great, I have no idea what any of those words mean. Google is your friend, Stack Overflow is your friend. If you don't know something, Google it or ask somebody who does. The way my class works at UW Seattle is I tell my students that if it takes them more than 5 minutes of getting the same error message, they should send me a chat message, because I use a Slack channel for my classes, or send me an email. 5 minutes, that's it. I say sort of the same thing for people in general. 5 or 10 minutes, if you really can't figure something out, ask somebody else. Your time is valuable. Too valuable to be spending hours beating your face against your monitor because you don't know how to use some arcane weird function in R. Anyway, in general, as you get better and better with R, the help files become more and more and more useful. Okay. But they always work the same way. Question mark, name of the function, that will be your help file. Okay, so R is a type of object-oriented programming language, meaning every single thing in R, no matter what it is treated as and stored as what is called an object. Object is kind of vague. It's a thing. It's anything in this programming language. So data, the functions you might run on data, the models, the output from those models are objects. Your plots are objects. A single number, an integer, is an object in R. Everything's an object. So if it's a thing in R, it's an object. So you probably want to know how to create, access, destroy objects, because that's everything in R. So creating an object can be done using what is called the assignment operator. The assignment operator is just a less than sign with a minus next to it, pointing to the left. It's an arrow. It works like this. I want to create a new object. I'm going to call it new.object. I want that object to be the number 144. So what I say here is new.object, assignment operator 144. It's nice, it's a little arrow. It's saying 144, let's just shoot you into that. New object is that. Operators, this thing here is an operator. It's kind of hard to see where I'm pointing here, but that's the assignment operator. Operators are a type of function that look like a symbol, and they usually sit between two objects doing something to either both of them at the same time or using one thing to do something to the other thing. There's a lot of different operators. So, yeah, they look different from other functions. Like most functions will have like a word with parentheses at the end. Operators actually can be used that way too. Like, I could take this assignment operator and do backticks assignment operator and then parentheses. We never use that way in R. So we do math with operators in R. X plus Y, plus is just the addition operator in R. It doesn't do it's not working any way fancier than this assignment operator. It's just, we have two objects, we have a symbol in the middle that determines the relationship between those two objects. The assignment operator just says, whatever is that object on the right up there, I want the object on the left to become that object. Okay? Yeah. So, if you want to call on an object, so you want to display what that object is, or the contents of the object, you could say, you just use its name. If you just type new.object into your console, if the object exists, you're going to get 144, because new.object is the number 144. Because it is the number 144, we'll see on the next slide, we can use it as if it really is that number. As a clarification for object names and things, object names can contain underscores and periods. They can begin period with a period or an underscore. The only restriction R has is you cannot begin an object name with a number. You can have numbers in them, you just can't start with them. It's very flexible. R is case sensitive though, so my opinion is just use lowercase everything. That way, because brains are much better at remembering spacing and spelling than they are capitalization. Just my opinion though. Some people love camel case, which is like every word in something begins with a new capital letter. I loathe it, but I let my students do it because I'm not that picky. So, good names will save you confusion later, and because you have autocomplete in RStudio, there's no excuse for not writing longer names. Long descriptive names are always better than short names unless they are absurdly long. Don't use sentences for your variable names, but don't use var1, don't use test1, don't use single letters. R will let you use a single letter. Don't do it, it's not informative. ID is fine though, that's a very informative two-letter one. We're good with that. Okay, so if you want to use an object, the object's name represents the information stored in that object. That information is that object. So you can treat the object's name as if it is whatever is inside of it. So for instance, I could take new.object plus 10, I will get 154. I could take new.object, add it to itself, 288. I could put new.object inside of square root, and because I picked a perfect square, you will get 12. The object is the number, right? It's pretty simple so far. Does that all make sense? Cool. Okay, now we're going to step up our object game into something more complex. So, vectors. A vector is a series of elements, such as numbers. Most commonly, it will be something numeric. You can create a vector and store it as an object in the same way that we assigned that single number to new object before. We will use a function C, which stands for combine or concatenate, to create a vector. It works like this. New.object is assigned to, or assigned to new.object is C 4, 9, 16, 25, 36. Taking perfect squares again. This just says we're going to take all of these elements that are inside of C, separated by commas to say that these are separate objects inside of it. We're going to concatenate them together. Then I called on new object, and what do I get? 4, 9, 16, 25, 36. That is the contents of it. The vector contains 5 elements, but it is itself still one object. It's a vector. Okay. If you name an object the same name as an existing object, R will not prompt you, R will not ask anything. It trusts you and believes you want to overwrite that previous object. In R, modifying objects is actually just overwriting that object with a slightly modified version of it. Overwriting is kind of poor. You just can shoot straight over stuff every single time. It won't complain about it. This is another reason to use good names for things. If you keep using var1, var2, var3, you might overwrite your var1 with a different var1 you didn't mean to and lose stuff. Nice names, it's harder to accidentally overwrite stuff. Okay. You can provide a vector like this new.object, as an argument for many functions that we might normally think of as only taking like a single number. For instance, I can take square root here, put new object into it, and it's going to return to me the square root of every number in that vector at the same time. It just operates over all of them. So here I get, because I picked perfect squares, 2, 3, 4, 5, 6. Does that make sense? Okay. Next, we often work with data that are categorical in some way. I teach primarily to social scientists, and like half their data, sometimes all their data is categorical. So if you want to create a vector of text elements, which are called strings in programming terms, so if you're looking for help about doing stuff with character data, call it strings, and that's when the programmers will come out of the woodwork to answer your questions. To do that, we want to place the text in quotes. So string vector here is going to be the same concatenate, the same combine command. In quotes, Atlantic, Pacific, and Arctic. If I call on this new string.vector, you'll see it just returns in quotes Atlantic, Pacific, and Arctic. The quotes are R telling us this is a string. Anything that's inside of the string, it could be anything. It could be numbers in there, but R doesn't recognize it as being anything other than a bunch of text. R will not do anything mathematical with a bunch of text. So it's like, okay, this is character data, it's something else, you're doing whatever you want with it. It can be arbitrarily long. A single element of character, there's no upper limit on the length except your RAM. So you could have a vector where every single one of those elements was an entire book, right? If you're doing certain types of analyses and text analyses, they might be whole paragraphs or something. It's still to it one text element, one little object. Okay. Categorical data can also be stored as something called a factor. Factors are categorical data with an underlying numeric representation. Models in R will usually automatically convert factors to dummy variables when you run models. So if you have a categorical variable that has like 5 categories in it, if you throw that into a regression model, it's automatically going to create 4 dummy variables for that without you asking it to do it for you. You don't have to create individual dummy variables, just use a factor. They do, however, have what's called an underlying numeric representation. They have levels. So you see when I do factor vector, I'm just giving string vector here to the factor command. It turns that into a factor. When I call on it, notice it's no longer in quotes. It says Atlantic, Pacific, Arctic. That is because those are actually labels on particular levels of this factor. The levels are Arctic, Atlantic, and Pacific. If I put this string vector into a linear model, the reference category is going to be the first level shown down there, Arctic. There's a command called relevel or recode that would let you change those reference levels if you want to. I'm not going to cover it in this, but it's good to know it's there. So categorical data you're going to use in a model, usually make a factor. I recommend waiting until right before you're going to run a model before converting to factor, because factors behave a little strangely if you want to try and modify them. Okay. Okay. So you can save and load objects in R very simply. To save an R object on your computer as a file you open later, the command is just save. You say save whatever object you want to save. And the neat thing in R is you don't have to save whole data sets. You could save a single object, you could save a plot, you can save anything. Any single object in R at a time can just be saved with the save command. Then you just save it and tell it where you want to put it. In this case, I said file equals new.object.rdata. .rdata is the base R data format for objects. There's also .rds, which works a little differently. I recommend just using .rdata all the time. It's good for saving whole data files. Something you'll notice immediately if you save a large data set in R files are very, very small. The reason is R stores them as a pure binary file. They're incredibly tiny. That also means they open really fast in R. So I usually convert things to R data files pretty early on and use it for that, unless it's something that's live updating, like sometimes I have CSV files that are constantly getting things added to them. That's fine, they're a little slower. You can open save data files just like this, load new.object.rdata. It will pop open that file that we just saved. Okay, so a question that should be obvious is, well, where are these files being saved and loaded from? Okay. The answer is they're being saved and loaded from whatever is your current working directory for R. So R saves and files and looks for those files in a current working directory. On your computer right now, if you want to see what your working directory is at the moment or by default, get wd parentheses will show what is your current working directory. When I ran these slides earlier, my current working directory was in my OneDrive, my GitHub, and my intro R workshop, which is the folder for this particular workshop. Yours will be something different. It'll be unique to every person probably because it's going to start with whatever your user is on the computer most likely. Okay? You can set a new working directory using setwd and give it some path. This obviously won't work on you because you don't have a CC-LAN user on your computer. Well, maybe you do, who knows. But yeah, you can set a working directory like this. So if you have different folders that are managing different projects, you can set your working directory and work in them that way. RStudio also has built-in project management features that will handle working directory things and stuff, but I didn't want to get into that today. There's a lot of things you can do that will actually make it so you don't have to set your working directory manually at all. I basically never do, but that adds some complexity. But this is how you manage your working directories. Does that make sense? How those work? And feel free also at any time to just wave at me when you're just like, you're speaking gibberish, and I will try and answer your questions. Okay, so talked about vectors. Vectors are sort of the building block of all files, all objects in R. Everything is either a vector or made out of vectors. But there are many, many more complex objects you can use in R. But you can use the exact same principles I showed for vectors to assemble all those objects. You can assemble them to things like matrices. Matrices are just essentially a series of vectors that form some sort of rectangular two-dimensional array. Arrays is a general term to refer to something that's at least two-dimensional, but can be 3, 4, 5th, 6th, 8th, 60th dimensional. You can have an arbitrarily large number of dimensions in arrays. Most people in the sciences don't work with anything over a 3-dimensional array. It becomes rapidly mind-blowing to start working with some things that are more than 3 dimensions, but there's sometimes good reasons to use multidimensional arrays. Lists are a type of vector where instead of every item in that vector being the same type of object, like a number, they could have like each one could be something completely different, including another list. Lists can be, we're going to get into a little bit here at the end of this workshop, you can sort of infinitely nest lists inside of each other, and that's how complex objects in R are stored. Things like the results from a linear model or an ANOVA are stored as a list because they are hierarchical and you can just dig way deep into them and they have all kinds of stuff. We'll see this in a little bit. And then data frames. Data frames are what I consider to be the sort of core object most people in the sciences or in research or are interested in. Data frames are R's representation, essentially, of a spreadsheet. It's a rectangular flat file of data where your columns are variables and your rows are observations. Because that's usually the most useful to probably all the people in this room, the rest of this workshop is going to be spent talking about manipulating and using data frames to do stuff. Okay. Got to maintain the high energy. Caffeine. Okay. Loading data frames. So, the easiest way to get external data, and by external data I mean something that's not already a .rds or RData file into the computer, is if it is a delimited text file. A delimited text file is just some sort of text file where you have different entries of data that are separated by something that tells the computer, oh, this is one entry, this is another entry, there's something in between them. Most commonly, we encounter a common Excel type format, which is CSV, a comma-separated value data format. Every element is going to be separated by a comma, and then every row is going to be separated by a line break. There's also TSV files, tab-separated files, there's space-separated ones. There's also fixed format files. Fixed format files are based on the idea of a punch card, where you have a certain number of entries horizontally. Once you hit, say, 80, which is a common punch card length, you'll hit 80 of them, you just go to the next line, you have another 80. If you do want a space between something, it has to be specified that the variable ends at a given location on that punch card and a new one starts over here. It requires what's called a dictionary. I'm not going to cover fixed files, but if you work with old data like I often do, it comes in punch card format. You've got to learn how to read in a dictionary for all that old punch card stuff. Magnetic tape reel data too, same thing often. Except sometimes it's up to 144 wide, which is a little different. Anyway. So, R has a whole bunch of built-in functions for importing data that is stored as raw text. So, common ones are read.table and read.csv. Read.csv is of course specific to comma-separated values. There's a read.tsv for tab. All of them are actually just calling back to read.table with specific options, being like, these data are a CSV, these are a TSV. If you get help on read.table, you can see all of the sort of different ways you can load in text data. I believe it's read.fixed for fixed data, but I'm not positive. I actually don't use the base ones, I have my own. Yeah. If you want to write those data out as CSV, so very commonly we're working in R, but we're working with lots of other people who are not working in R. Nice thing is it's really easy to write out files other people can read, so if nobody you work with works in R, you can very comfortably always work in R. I work with a lot of people who do not work in R, like faculty mostly, and it doesn't matter. They never know because they're just going to get a Stata file, an SPSS file, a CSV file, or something just because I read and write those into my R, I put them back out. Doesn't matter. You can also have a single platform. So I've got one particular, I manage the Denver Youth Survey at UW Seattle, and I'd say there's maybe 6 or 7 programming languages and software packages used for the general complete cleaning and maintenance of that data set, but I manage them all from R, so I call out to all that other software and it just runs it in the background and it comes back to my core R. It talks with everything very easily. I like it. Cannot say the same for, like, I would not be able to manage a whole bunch of R stuff from inside of Stata or SPSS or anything like that. Anyway, everything speaks to each other nicely. Okay. By default, these functions, read.table, read.csv, if they encounter a column of character data, they're going to read it in as a factor, that object type I talked about a bit ago. Often because factors are a little bit harder to use for something like data manipulation, we often don't want them to come in originally as a factor. This is very common if say it comes in but it's messy text, the punctuation is messed up, or sometimes it's not a meaningful factor. Sometimes it's actually something you want there to be text, like sentences or something like that. You want it to be text. There's an option in all of the read.table, read.csv functions called strings as factors equals false. This is what I talked about. This is what camel case looks like. The capitalization of the A and the F. I hate camel case, but that's a lot of base R functions are in camel case. It upsets me greatly. But strings as factors equals false will load them in as character data instead of factors. I basically always use that because I want to sometimes massage that data a little bit. I'm just like, I don't like the way it is. What you get?
Do you always have to include the .csv in the file name?
Yes. Yeah, it wants suffixes on files, for sure. If it has no suffix, if it's read.csv, of course you don't have to. If it's like some spreadsheet and it has no file suffix, of course you don't have one. Which is something that happens sometimes. I receive like a CD in the mail from ICPSR or something, and it just, like, the data are just a file with no suffix and no explanation. ICPSR doesn't do this anymore, but it's happened to me in the past, and you're just like, I have no idea what these are. 99% of the time, it's actually a text file. You open up in a text editor, you'll see, oh, I can see what format that is, and then load it in with the appropriate R command. Okay, so often we want to load data from other software packages, so something that isn't a CSV file or a TSV file. So if you're working with people who use Stata, SPSS, or SAS, or you yourself use these, and you want to slowly migrate your stuff to R, which is the most common thing. It took me a little while to go from, I used to teach Stata at Oregon State University before I came to UW, and I started teaching myself R, so I slowly migrated my stuff over. So I had to commonly go back and forth between Stata and R files. There's packages to do that. So you can use a package. Next slide's going to talk about what packages are. So there's packages in R that are called foreign, and then Haven is an add-on one you have to download. These ones are for loading files from these other statistics packages. They use functions like read.spss for SPSS files, read.dta for Stata files, read.export for SAS export files. These ones are not very complex. They tend to just work, and they work really easily. Sometimes they will lose a little bit of metadata. What I call metadata are things like R doesn't have a native way of doing labels on variables. Variable names, yes. Variable labels are a little bit weird in R, and you have to do some hacks to add them on. Read.dta will sometimes lose overly long variable labels. It's not usually a big deal, but sometimes it is. The Haven package, which is part of the packages referred to as the tidyverse in the world of R, which are actually sort of the modern standard for doing data manipulation and plotting. ggplot2 is part of the tidyverse. dplyr, if you've heard of that, is part of the tidyverse. Haven package has functions read_SPSS, read_DTA, and read_SAS. Those are a little bit more complex, but they keep every little bit of metadata from that. Every little bit of label and Stata, all that kind of stuff is all kept from those. They're a little harder to use, but if you need everything, that's the way to go. For less common formats in these big statistics packages, Google it. Like I said before, I have yet to encounter a data format I couldn't open with some R package or some very easy, clever hack to get it in. Nothing. And one of the big reasons that this works is because almost everything actually stores its files as some sort of raw text. Anything that's in raw text, you can always get into a computer somehow. Things that store stuff is not raw text, some kind of weird binary. Word files are like this. They're actually a binary. Word is an evil, horrible program. Don't use it. It's hard to load things in from it without some sort of interpreter. Anyway, if you encounter what I call an ambiguous file extension, we have a file that ends in .dat. Well, everything saves something with a different type of .dat. What is that? Open it with some good text editor. Good text editor being something that doesn't crash when it's fed a 1 megabyte text file. Something like Atom, Sublime, there's a couple other ones. I don't know what the Mac equivalent ones are. I mean, Vim or Emacs if you're one of those people, but you're probably not in this room if you use those. Most of the time, an ambiguous file like .dat is actually going to be some delimited or fixed format text file. And you can figure out how to load it with the conventional things. If not, you find something truly weird and you can't find any information on it, remember, email me, let me know. I'm excited about it. Okay, but what are packages? So if we want to use foreign or we want to use Haven, we have to load a package to do it. The foreign package for loading those files is built into R, but by default, you can't access its functions. Haven is something you would have to install. These are packages. R is all about using packages. So, packages contain functions and sometimes data, very often example data sets, created by the community. All the power in R is coming from add-on packages. So, for the remainder of this workshop, we're going to use a package. We're going to use data that are in the Gapminder package. These are data, it's a panel data set on countries, things with their GDP, their life expectancy, their population from the years 1952 to 2007 for like 144 countries that were assembled by Hans Rosling's Gapminder project, and these ones have been cleaned by Jen Bryan up at UBC, who's one of the premier people in the R community. Anyway, these are great data for doing examples of a lot of things, because of panel data sets, there's a lot of things you can do with them. Anyway, they are in the Gapminder package. So in R, if you want to install a new package, the function is very easy. It's install.packages, and then whatever's the name of the package in quotes, it must be quoted. The reason for this is you're not looking for an object called gapminder on your computer, you're giving it the name gapminder, and it's going to go do a search at what is called the Comprehensive R Archive Network, which is where you probably all downloaded R from. It's going to go look for a package called that there. It's going to download it, it's going to install it on your computer. You only need to install a package once for any given version of R, or when that package updates, which means you generally never put install.packages inside of an R script you're going to run a whole bunch. You just install it once. Install.packages is something you usually put in the console. Or if you want to have like a script file that has an installation of everything that you just run every time you update your R. Because if you update R from 3.5.1, current version, to 3.5.2, imminent, you want to reinstall all your packages. For somebody like me who has 400 or 500 packages installed, it can be kind of annoying to manually install them. Usually instead I treat it like cleaning my closet. If I don't use that package for a long time, I'm glad I didn't install it, so I just reinstall them manually each time. Yeah. Okay, loading packages is very easy in R. The command is library. Say library gapminder, it will load the gapminder data set. That's it. If you want to load other packages, you can do library foreign is the package for opening SPSS SAS files, library haven if you'd installed it for those kinds of files. Once the package is loaded, you can now just call on the functions in it as if they were any other R function. You don't have to specify, oh, that was in the gapminder package. You can just say data gapminder will place that data in your global environment in the top right. If you do that, it's going to do something a little funny. You're going to see gapminder pop up in the top right, and it's just going to be in angle brackets. It's going to say promise. This is because R does something called lazy evaluation, where until you actually ask for that data, it doesn't load the data. If you want to see something funny, type gapminder, but don't even hit enter after you've loaded the data. You'll see as soon as you type that R for gapminder, that promise flicks to being the whole data set, because it anticipates, oh, well, he's about to ask for it, so fine, I'll load the damn thing. Lazy evaluation is a way to save little bits of RAM and little bits of processing power for a programming language. It's a way of being efficient that's usually completely behind the scenes. Almost every programming language has a little bit of lazy evaluation nowadays. That's the only time in R you'll ever actually see it. But it confuses the hell out of my students, so I make sure to always note it. Okay. The function head on any object will display by default the first 6 elements of that object. What an element is depends on what the type of object is. So gapminder is, well, technically it's a tibble, which is a type of data frame, but it's a data frame. If you do head gapminder, this is what you see. You see all the variables: country, continent, year, life expectancy, population, GDP per capita, and you see the first 6 rows. They're all Afghanistan. Afghanistan is alphabetically the first. You see the year, 1952, 57, 62, 67, 72, 77. It's a panel data set. So it has multiple countries, and within each country, multiple years, right? Okay, and also says the type of variables these are. Country is a factor, continent is a factor, year is an integer, life expectancy is something called a double. It's a double precision numeric variable. Population is an integer, GDP per capita is also a double. Does that make sense? It's pretty straightforward so far. Okay, and we're on track on time. I'm liking it. Okay, indexes, indices, and subsetting, and dimensions. So, in base R, there are 2 main ways to access elements inside of an object. They are square brackets and dollar signs. How you access an object depends on the number of dimensions that object has. So for instance, data frames always have 2 dimensions. They have rows and they have columns. That means you need to provide, when you index them or subset them, you must provide 2 dimensions. Square brackets will allow us to numerically subset a data frame in the format like this. Object, row, column, or columns, are row or number of rows, and column or number of columns. First element in this subsetting, in these brackets, is the row. The second is always the column. Okay? If you leave the row or column place empty, it will return all elements of that type. So for instance, if I do gapminder in square brackets 1, nothing, or a space, I'll also treat it as nothing. R ignores spaces, it's totally space insensitive. This will return the first row of the gapminder data set, but every column of the data set. Does that make sense? Okay. Here's another example. Now, I wanted the first 3 rows and the 3rd and 4th column of the data set. I do something a little different here. I say 1:3 and 3:4. The colon operator in R creates a series of integers. It creates an integer vector that goes from the first argument, so in this case 1 colon 3, that's from 1 to 3, which means it's going to be the number 1, 2, and 3. It's a good way to subset sequential columns. If I wanted, say, the first 50 rows in the first 2 columns, I could say 1 colon 50, and then 1 colon 2 will give me first 2 columns, first 50 rows. Does that make sense? Okay. And it is just the equivalent of if you did it in C. You could do C 1, 2, 3, 4, 5, 6, all the way up to 50. It's exactly the same. The colon operator is just a way to save you from typing. Okay. So, data frames and names. You can also subset columns in a data frame using the names of that column using the $sign operator, which is referred to as one of the extract operators. This returns the column as a vector. So what I did here is I said gapminder $sign GDP per capita, and then I subset that again. So GDP per capita, if I do that, it's going to return that column as a vector, not a data frame, but it's just going to be popping out as a vector. You can, if you want, double subset something. I can say, okay, I want that GDP per capita column, but then I only want the first 10 elements, the first 10 observations of that column. So I did 1 colon 10 afterwards. You notice how up in that bracket I don't have a comma, because the thing I'm subsetting, gapminder $sign GDP per capita, is a vector, and vectors have 1 dimension. They only have length. So I didn't have to put a comma because I'm only subsetting 1 dimension. If you try and subset something and you get a warning like incorrect number of dimensions, check to make sure that you're using 2 dimensions with a 2-dimensional object or 1 dimension with a 1-dimensional object. It can be a little bit tricky, but and in general, reading R error messages can be very tricky. What you learn to do is ignore the fact that it's a large pile of red text. Look for keywords. You just look through and be like, blah, 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 blah. You might see the name of a package or the name of a function. You're like, well, I know it's there. Or you'll see some keyword like subset dimensions, you're wrong and bad, and then, that kind of thing. You just learn how to read, but only through experience do you learn how to read these error messages. At first, it's okay if they're like, I don't know. You can just copy the entire error message, paste it into Google. Someone has encountered your problem. Pretty much always. Okay. Yeah. Does that make sense? Very straightforward. Okay. Next, we can index by expressions. This is where we're starting to get with actual programmatic stuff. Okay. We can index using expressions. Expressions are a logical test. In this case, I say, I want gapminder, the whole data frame. I'm not doing $sign, I'm saying I want the whole data frame. But I only want the rows where year is equal to 1952. So I say gapminder $sign year, because I'm looking at only the year column for that, equals 1952. Equals is check if these things are equal. If you just use equals, that's a very different thing. That's actually a different version of the assignment operator. Just remember, you need 2 equal signs to test inequality. Notice I put it in the rows place in the brackets. That's going to be me looking for rows where gapminder year is equal to 1952. It's just going to give me those rows. And then I wanted every column. So I see here there were 142 rows with the year 1952. So year 1952 is there all the time. A very logical question one could have after that is, what the hell is gapminder $sign year equals 1952? What is that thing? What does it look like? Well, the answer is, it is just a series of trues and falses. What's going on here, so what I did here is I did head 50 to display the first 50 elements of it, because gapminder is a really large data set. I don't know if I see the first 50. So, gapminder $sign year equals 1952, what that is doing is it's looking at, okay, we have this gapminder year column. It's really a vector, but let's imagine it vertically. Then what it does is it goes down every single element. If it sees a 1952, it returns a true, which is that first true there because the data set starts in 1952. Anytime it sees something other than 1952, it says false, 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 false. Oh, another 1952, true. It continues to the end of the data set doing that, which is why this is just true, false, 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 true, and so on and so forth. The way subsetting works in like the subset operator is it will return data anytime a true is in that subset operator, and it will get rid of it anytime a false is in that subset operator. So you can use logical expressions like this to select individual rows or elements of anything. This is a little bit more complex, but does it kind of make sense? Is it intuitive? A true means you want it, a false means you don't. Okay? something to play with, create objects or load objects and see what happens when you try different combinations, and see what that actual logical statement is producing in terms of trues and falses. All computing is built from the very ground up on trues and falses. Ones and zeros are just trues and falses. This is kind of nuts and bolts. But if you know how to do this, you can do everything just using trues and falses.
Quick question. So
Yeah.
in the code before, where it was just equal 1952, comma blank, is that return all entries?
Mm-hmm.
Okay.
It's going to return all columns. Yeah.
Columns, okay.
All columns, but only the rows where a true appears.
Okay, got it.
Yeah. So usually you would use basically that thing in the row column or in the row place needs to have as many elements in it as there are rows in the data set. You can't like subset a data set with 1,000 rows with something that has 5. It's going to be like incorrect dimensions, like I was talking about. But yeah, if you're subsetting using an actual column in the data set, it's always going to have the same number of observations. So this is a normal way to do it. You can get crafty and subset using different objects if you get deeper into this. Okay, so logical operators. Equals equals we just use for testing if gapminder year equals 1952. But there's a lot of other logical operators we can use to do these sorts of operations. There's tons of them. There's a link you can click on and see them all. Not equal is the opposite of equals equals. This is going to return a true every time they are not the same thing that you're looking for. So if you said not equal to 1952, it would be a false. It would drop all the 1952s and return every other year. There are greater than equal, less than an equal. So for numeric things, you can do numeric comparisons, right? There's percent in. Percent in is used for checking multiple conditions at the same time. It's like equals equals, but it can accept multiple things on the right. It's a little bit more complex, and I'm pretty sure I cut the slide on this, but look into using this. It's neat. So if, instead of saying something like equals equals 1952 or year equals 1957 or year equals 1962, you could just say year percent in 1952, 1957, or 1962. It works exactly the same way as a bunch of ors, which I'm going to get to in a second. You can also combine multiple logical conditions. Maybe you want 1952 and Afghanistan. You put those two statements together with an and in between them, and it will require both of those to be true to return it. You can do or. This will require one or both of them to be true to return the item you ask for. There's also exclamation point here, which will invert a logical condition. Let's say, and this sometimes happens, you can figure out a way to subset your data in a particular way, but the only way you can figure it out is how to get everything you don't want. Well, if you put an exclamation point in front of that entire statement, it will give you the exact opposite. Sometimes it's easier to think of counter cases than the cases you want. Just flip it with an exclamation point and don't waste time trying to think of the positive selection case. Another one to play with. It's a little weird. It turns every true to false and every false to true. Okay, so logical operators are one of the very core foundations of all programming. Experimenting with these and becoming familiar with how they work is key to programming in any programming language. It's all logical operators until you get pretty deep into it. Okay, so a side note. Missing values in R are coded as NA. You notice instead of being like NA in quotes, it looks like a number, NA. That's because it's reserved value for a not available value, okay? Even one NA in most functions will poison the well. That is, you will get an NA back out of the function. This is because unlike something like Stata, R assumes that NA is something that you actually care about. It doesn't just ignore them unless you ask it to ignore them. That's something, a behavior I don't like in packages when they're just like, oh, well, if there's NAs, we'll just get rid of them without saying anything. You might actually have 95% of your data be NAs if you're not watching your sample size or something, and it just gets rid of it without saying anything. Oh, that's really bad. That's really bad. R will scream bloody murder at you if you give an NA to something that without specifying, okay, I know there are NAs. This is a check on you. For instance, let's say I want the mean of a vector. That vector up there, which I did 1, 2, NA, 4, 5, 6, NA. If I try and get the mean, it puts out an NA. It says there's an NA somewhere in there. You cannot get the mean of something where one of those things is not a number, right? Because a mean is just the arithmetic mean of a set of numbers. But if I say mean, that vector na.rm equals true, na.rm stands for not available values, remove. na.rm true, it removes the na of the na and gets the mean of 1, 2, 4, 5, and 6, which is 3.6. That make sense? Many functions in R. Oh yeah, what you got?
Could I also use code to say, okay, for every calculation from now on, this should be true, or do I have to retype it every time?
Actually, technically, you could probably set baseline in your R options. You could make it so all na.rms default to true. I would generally recommend not doing that and doing one of two things, which is either subsetting your data so you explicitly removed your NAs, or just manually doing na.rm true. If you don't want to type all of true, you can at least say na.rm equals t. T stands for true. But in general, good R practice is explicitly saying everything. You write a little bit more, but it reduces the number of mistakes. I try not to change my defaults because in my experience when I was first getting into R, I would do things like change the defaults, but then I just forget about them and I send my code to somebody else. Their defaults are then not the same as mine, and everything breaks. And they're like, why is this breaking? It's like, well, I'm picky, you know, that kind of thing. And that's what happens. Yeah. But yeah, you can. Okay, another one. You cannot test for equalities with a missing value using equals equals. NA will always return an NA for all logical conditions. If I do vector missing equals equals NA, well, it just says NA for everything. None of them are. I can't use NA on either side of that equality. You can, however, use a function called is.na. Is.na vector missing will return a false if it is not an NA, and a true if it is an NA. That's how you find missing values. That argument over here, mean vector missing na.rm true, is exactly this written out using the is.na. Mean vector missing subset is.na vector missing, exclamation point reverses that. So I find every element of that vector that is missing, and that would by default return a true. That would keep only the missings. If I reverse that using an exclamation point, it's now dropping all of the missing values, keeping the non-missing values, and calculating the mean with them. na.rm is a shortcut to save you from writing out that kind of subsetting statement. Okay. It's okay if that's confusing. There's a bunch of things going on there. But you can always look back at the slides, look back at the content, figure out how it works. For some people, it's just like, oh, that's obvious how that works because they have a mind for it. I definitely did not when I started this. Okay, so multiple conditions is something we very often want. Let's say we want all the observations in the Gapminder data from Oman after 1980, but through the year 2000. We can do it like this. Gapminder and then subset. Gapminder $country equals Oman. Gapminder $year greater than 1980 and year less than or equal to 2000. Comma space meaning we want every column. What do we get? Only Oman and only those years specified. That's how we do multiple conditions. You can just chain them together for an arbitrary number and it will get the union of all of those conditions using AND. Yep. Note here that in all of these I'm doing Gapminder $Gapminder $Gapminder $. In base R programming, you always need to use that full object name when you're doing subsetting. The reason for this is because R can have multiple data sets loaded, and sometimes you want to do something like, let's take these Gapminder data and subset them using data from an entirely different object. So I could say something like Gapminder and then other data $some variable. You could subset from completely separate objects. If you don't like typing those Gapminder $ and stuff, I would recommend going to something like dplyr, which is a alternate way of doing data manipulation in R, where you tend to type a little bit less and it has a little bit more intuitive syntax. I teach base R in this workshop because this is going to be everything you need to get started for all the basic operations for data manipulation, analysis, and everything like that. Getting to the tidyverse, the dplyr, and stuff like that, it's a little bit more complicated and it would be impossible to squeeze into an hour and a half. This is tough enough to squeeze into an hour and a half. Okay. So, yes?
So the other data comes from a different data set than Gapminder?
It could.
It could.
It could. Yeah, if it doesn't exist. So this is just an example, but you could totally have another one. You just load in another data set and use that. If they were the same length, like if they're the same number of rows, you could subset one using the other. Very commonly, you'll do something like extract part of your data set, do some operations on it, and use that data set to subset the original data set. R doesn't care. You can just, everything is just an object, everything is that. You can get, and also commonly maybe you don't even want to use a data set at all. No data frame, you're just using vectors and subsetting different vectors. Just use each other. Yeah. It's because R is a programming language rather than a pure statistics package. So it just is like, objects are objects. You can do whatever you want. It's pretty freeform. Okay. So saving a subset. If we think a particular subset is going to be used a bunch in our analyses, we probably want to save it as its own object. So what I've done here is I say, okay, I just want the observations that are in China. I say Gapminder, and then in brackets, Gapminder $country equals China. If I get head on the China object, it's just the observations in China. But now, you see, I can call on it using the object name China. So if you have some subset you want to use, just make its own object if you're going to keep using it over and over again. I recommend not creating too many, like a whole bunch of objects in a global environment. It kind of clogs it up with stuff, but you can create as many as you want. And basically everything you create in R is going to pop up in your global environment and name the same way. Data works the same way, and you can subset and create it that way. It's pretty easy. Okay. A common thing we might want to do is we might want to subset rows down in some set. So in this case, I'm saying, okay, I want all the countries that are in former Yugoslavia. That's Bosnia and Herzegovina, Croatia, Macedonia, Montenegro, Serbia, and Slovenia. To get that, I'm going to say, I want to create an object called Yugoslavia, which is gapminder, and then gapminder $country %in was the thing I talked about before, in former Yugoslavia. Well, what former Yugoslavia is an object that is the text of the names of all those countries I want. It's going to return a true in my subsetting function when it encounters any of those names. As a result, Yugoslavia now contains, in this case I've shown only the Bosnia and Herzegovina ones, but it also has Croatia, Macedonia, Montenegro, Serbia, and Slovenia as observations. This is just a faster way than typing a whole bunch of OR statements, like I said before. Okay.
Quick question. So if you were working in one data set, like only in Gapminder, can you tell R, I'm working in Gapminder,
Yes.
so you can stop?
It's called attach. So if you take that gapminder and do attach on it, it will take all the variables and put them in the global environment. As long as you are only ever working with that one data set in that particular script file, you can do attach. I don't teach it because it's considered bad R style to do that. But yeah, no, you can absolutely do that. Okay. Okay. So maybe you want to create new columns in your data set. Very often we want to do this. We create new columns in DataFrame using the exact same subsetting functions that I already introduced. If I want to create a new column called Yugoslavia pop million, so it's population in millions, I just say let's assign to pop million, and that $pop million doesn't exist yet. It will be created once I assign to it. Yugoslavia $population divided by 1,000,000. I can do life expectancy past 40 as a demographer. This is not the correct way to calculate your life expectancy past 40, but we'll accept it for now. Yugoslavia $life expectancy minus 40. I get head on Yugoslavia. We can see my new population in million variable I just created, which is just equal to population, which is in scientific notation right here, divided by 1,000,000. Same thing. And then because of the width of this data frame, it's actually cut off my life expectancy past 40. I've left that there as an example that if you have it too wide, it's going to cut things off just to save space. Okay. Does that make sense how I'm doing my assignment? It's the same as subsetting. All the tools they're bidirectional. You can extract things or you can make things using the same things. Okay. Chugging along, we got 23 minutes. Okay. If else. This is a powerful function. A common function used in general R programming is this function if else. This returns some value based on the logical test. So you put the same kind of logical test in that test section of this as you would for like a subsetting thing. The difference is instead of just returning trues or falses, the if else is going to convert the trues into a particular value and the falses into a different value. Just sort of a quick way to do that. The way it works is that if else will return whatever value you assign to yes. In this case, 1, if the statement x equals y is true. It will return the second value if that is false. And if you give this an NA, so if the test comes out NA, it returns an NA. Like most things in R, if you give it an NA, it pops out another NA. Okay. Here's how it works. Let's say that I want to create a new short country name in my Yugoslavia data frame because I'm really tired of typing out Bosnia and Herzegovina every single time I want to use that country. So I'm going to shorten it down to just B and H. I say, if else Yugoslavia $country equals Bosnia and Herzegovina, get B and H. If not, as character Yugoslavia country. Remember that country was originally a factor? That text up there I'm producing is character data. I want to pop out as a character. So if you're ever messing with factors and you get something like, oh, this is the wrong data type, use it as characters to begin with and then convert to a factor later. That's what I'm doing here. I'll give an example of factors on the next slide. Anyway, so I've created that new one using the if-else statements. What this does, by having it so that if it's true, it makes it B and H, but if it's false, it just returns the original data. This is how I don't modify anything except the things that return a true. I just want to change Bosnia and Herzegovina. I don't want to change anything else. The result is that I now have, so this is my original country column and my short country column. The only thing that's changed is Bosnia is now B and H. If else is a good way to do simple recoding, or say you want to create a binary variable. You have a whole bunch of different categories, but you really don't care about the difference between one value of that and everything else. If else. Okay. Does that make sense? It's the simplest way to change a single value. Another thing you'll notice here about R, I broke up that if-else statement into 3 different lines. R will continue running code as a single line of code so long as some line ends in something like a comma. Because the comma separates arguments, so you can put each argument on its own line. Just break it up for readability. Okay, so we're in the final section. 20 minutes to go. We're dead on pace here. So let's get into some analyses. I've given you all the basic tools, like really all the base R tools you would need to take data, subset data, shape it, create new columns and things. About the only thing I didn't cover is aggregating data, which tends to be a very complicated operation in base R. Really easy in the tidyverse. I recommend my slides for that stuff if you're interested. Anyway, now we can use everything we know to say assemble data sets, modify them, produce some sort of analyses. Most people, they're going to be doing, honestly, most people's work in the sciences, especially in like social sciences, it's 80 to 95% munging data, dealing with your data, right? It's usually a small amount actually running the statistics, at least in my experience, and I'm basically like a perpetual RA for people because of like all this. I still spend 95% of my time messing with data. Small amount of time running analyses, because if your data are formatted properly, it just runs, right? But didn't know how to know stats. So, first thing I'm going to show, histograms, a very common operation on some sort of continuous variable. We can use the hist function in R to generate a histogram of a vector. You have to give it a vector, right? Because it's only a single variable. In this case, what I've done is I said gapminder $life expectancy, and then I've added a couple extra arguments here. So that hist gapminder $life expectancy is all you need to generate a histogram of life expectancy, but I wanted to pretty it up a little bit. So what I did is I added xlab equals life expectancy in years, and main equals observed life expectancies of countries. Main is the title for the plot. xlab is the x label down here. By default, the y label is frequency. I was pretty happy with that. It comes capitalized. I'll stick with that. If you want to know other options for the histogram function, like what size bins to use in the histogram and that kind of thing, question mark histogram will give you all the options. There's a lot of options. In general, plotting with base R stuff can be quite simple like this. You want some basic quick graph? Hist pops up. Okay, scatter plots. So, base R scatter plots are the default behavior of the plot function in R. So you just say plot. As long as you don't tell it to do some other type of plot, it's going to pop up as a scatter plot. In this case, I've said I would like a scatter plot of life expectancy by GDP per capita. The life expectancy tilde GDP per capita up there is what is referred to as a formula in R. A formula object is what you give to some plotting functions and most modeling functions. The y variable or dependent variable is on the left side of the tilde. The independent variables or variable are on the right side of it. It's just like a regression formula. Imagine that tilde is an equals and it's y equals x1, x2, x3, x4, x5. Scatter plots only take 2 variables, one on the left side, one on the right side. I could also, instead of life expectancy tilde GDP per capita, say x equals GDP per capita, y equals life expectancy. Plot will be happy with that too. But I want to introduce formulas, so there you go. Okay. Other things I've added to this plot is the way our base graphics work is if you can keep adding things to a single plot just by running another command as long as that new command doesn't generate an entire new plot. So I generated this overall plot which has some nice labels to it. PCH there makes the dots a certain size. I did 16-point dots. And I did log equals x. GDP per capita, the demographer in me, I was not able to not log it. I was like, it must be logged. So I logged it because I knew it's a log linear relationship between life expectancy and GDP per capita. So I just said log equals x. It automatically scales that x-axis into its log scale. Then what I wanted to do is like, oh, okay, let's add a couple things. AB line is the base R function for generating single lines that you can stick onto a plot. In this case, I used 2 arguments, different arguments in each line. AB line H equals mean gapminder life expectancy. H stands for horizontal line. The horizontal line will be given a y-intercept equal to its argument. The argument I gave it was the mean of life expectancy. and then made it fire brick red. So now we have a red line that goes through the mean of life expectancy. So that line right there is crossing through the arithmetic mean of the Y data. And then I did the same thing, but the argument is V for GDP per capita. There's a vertical line going through the mean of GDP per capita. It doesn't look center of mass because we're on logged data, so it's going to be shifted up a little bit, but that's how that works. Pretty simple. I recommend toying with it. Next, formulae in general. So most of the modeling functions in R and many of the plotting functions use a common format for formulas. They're an object like anything else. If I say new formula equals, so new formula assigned to that y tilde x1 plus x2 plus x3, I call on that object. It just looks like that. It looks like exactly what I put it in. It's not in quotes or anything. It's a special type of object in R. If I do class is a generic function in R that will return what is the class or type of object that you give it. It's good for diagnosing something like, I don't know what the hell this thing is. Get class and it will give you a whole bunch of information what the object is. It says it's a formula. Formulas are a specific type of object. R knows what to do with formulas in many different functions. Anyway, as I said before, dependent variable goes on the left, independent variables go on the right. If you want to know way too much about formulae, click the link there. You'll have pages and pages of explanation for all the different ways they work. They get really complex and more complex things, like you can, hierarchical linear models will have functions that have, like, each level of the model will have its own parenthetical part of the formula, stuff like that. I do a lot of structural equation modeling, so the formula objects will be really, really long because you're specifying every single one of the equations and stuff like that. They get big, they're all formula objects. Okay, simple tables in R. The function is table. You give it 2 or more vectors, and it will create a cross tabulation of whatever you give it. If you give it one vector, it will do a frequency table of that one vector. So in this case, I used a different data set that's built into R, so you'll see you can call on mtcars without ever loading a package or anything. It's an example data set built in. Anyway, I just said I want a cross tabulation of cars by the number of cylinders in their motor and whether they're an automatic or manual transmission in this particular data set. And it gives me a little cross tabulation. It's super bare bones. It gives by default no tables or no titles or anything. It's just saying that, oh, okay, the second variable is on the top. The first variable is on the side. Those are the values of it on the margins, and then those are the frequencies in the middle. It's just a plain old table. You can dress them up with all sorts of options, but that's the base. One of the nice things about a base table like that with no additional things modified, you just can send that straight into a chi-squared function and run a chi-square on the table that you just ran. So if I take the output from table, I could save that table object and then put it into chi-square.test, or I can just put that call. So I put the table call inside of chi-square.test. It's going to run a quick chi-square test on it. It's going to give me a lot of information, actually. Here it runs a simple Pearson's chi-squared test. It tells me what is my value here, my degrees of freedom, the p-value calculated here. It's also going to send out a warning up there that says chi-squared approximation may be incorrect. The reason for that is because mathematically speaking, your chi-square p-value in most cases is going to be slightly inflated. If you're into stats, probably aware of this. You can rescale it using an argument rescale.p equals true, or you can turn it into a Fisher's exact test by doing simulate.p.value equals true. Your p-value will go down just slightly. Most people don't care too much about that, but if that warning over there drives you nuts, I recommend just doing Monte Carlo simulation with the simulate.p-value equals true. It won't slow your computer down, it's very efficient. Well, unless you're doing a table with like 10 million observations, but if you're doing that, you probably know what you're doing already. Okay. Next, t-tests. We commonly want to be able to do t-tests. It's very easy. Gapminder by default did not have a binary variable for me to do like a 2-group t-test on, so I created one really quickly. I said, I just want to split my data into before 1980 and after 1980. So I created a new variable called post-1980 that takes a value of if else Gapminder year is greater than 1980, give it a value of 1. If it is not greater than 1980, give it a value of 2. Good on 1 and 0, doesn't matter, do whatever I want. Okay, the function for t-test is t.test. And then it takes a formula object, that's kind of hard to see because of the little line right there. It's life expectancy $ post-1980. So the dependent variable is life expectancy. The grouping variable for the t-test, what it's going to do a mean comparison across, is post-1980. And then I say data equals Gapminder. It takes a data argument. So it just says, oh, I'm going to look in the Gapminder data. I'm going to use this formula. I'm going to calculate a test. What we get is, by default, a Welch's unequal variance two-sample t-test. People who like lots of words. It gives me a t-value on the left, degrees of freedom, estimated degrees of freedom, they're adjusted for the variances, and a p-value. What this is saying to me is that the mean, in group 1 is 64.37 as life expectancy in post-1980. Before 1980, the mean was about 54.5, and then there's a 95% confidence interval on that t-test. Provides you most of the information you probably want out of a t-test. Pretty simple. Okay? Next, linear models. Linear models are very easy to run in R because it's sort of the bare bones base thing for very many statistical operations. We can run an ordinary least squares linear regression in R using the function LM for linear model. It has the same syntax as all these other statistical things that I just showed you. LM, life expectancy by population, plus GDP per capita, plus year, plus continent. This is just saying y equals x1, x2, x3, x4. It's just the formula there. Data Gapminder says look for these variables inside of the Gapminder data set. Run my OLS regression. Now by default, what you're going to see here is probably a lot less output than what you would expect from a linear regression. All you see is the call, which is the formula you gave it, and then a list of coefficients, no other information. You see the intercept, you see the base coefficients for all these variables. Notice here I gave it continent as a variable. It automatically split it into dummy variables for me. It knows it's a factor and it's like, well, it's categorical. Let's break it into dummies. So I have Americas, Asia, Europe, and Oceania. Okay, it breaks it up. So the thing is though, is you're like, well, how useful is this to me? I don't even have standard errors, I don't have p-values, I don't have any of that kind of stuff. Well, the reason for that is because R is actually creating a really, really huge object when it runs a linear model containing hundreds and hundreds of things. But it only displays the coefficients by default. What you can do is you can create an LM object or just put that LM call inside of summary. Summary is a broad command in R that does something totally different for every function you give it, but it summarizes whatever that thing is that goes inside of it. This is what you get if you run summary on a linear model object. This looks a lot like stata output. Now, I have things like, I have my residuals up here, I have a full coefficient table, lists all the variables, the parameter estimate, their standard error, the t-value, their p-value, with significance codes down there, residual standard error with degrees of freedom, r squared with adjusted r squared, and f stat with its p-value. Everything you usually get on a stata output, right? So most of the time, if you just want to see like this stuff, you'll do this with an LM. Okay? Thing is though, there's a lot more than that in that object too. So, LM produces a ton of information like every other statistical operation in R. If you want to see everything that is produced by that LM object or that LM function, you can do STR. STR stands for structure. It gets the structure of an object. It's sort of a way to display everything inside of an object in a nice like hierarchy. So what LM creates by default is a lot of things. I've actually truncated this because there's more than 13 individual things being produced at the top level. So there's coefficients, yeah. There's a residual, the residual for every observation in there. There's estimated effects. There's the rank of the matrix that went into it. It has the fitted values inside of it already. You don't have to make another call to like get the fitted values. They're already generated. It has everything. It has all sorts of things that are around optimization values and rank and some matrix properties of the model matrix used to calculate it. Tons of stuff. If you want to extract anything, it's in there. It generates everything. This is called a list. The way lists work is they're kind of like a vector, but every element could be another list or a vector or a data frame or anything. So, and they're hierarchical. So you can actually see here, I could do LM out, $QR, $QR, $something else, and navigate all the way down in this list. They're huge objects. Most people who use R don't really have to delve too deep into here, but if you do a lot of like serious statistical work or you're writing your own statistical methods, you're going to get deep into these objects and do stuff with them. The nice thing is R just puts them right at your fingertips. It makes everything, it's right there. Okay. We can access them, like I said before, using $. So if I say LM out, the original LM object I created, and do $ coefficients, I get out just that coefficients thing that was generated by my original LM object. If I do summary LM out and then $ coefficients, this is the coefficients object produced by summary. This is the one that has the standard errors, the t-values, and the p-values. This is a matrix. I could subset and get an individual element out of there if I want. When I make a dynamic document that pulls out coefficient values and automatically fills them in as values like in my paper, so if I'm writing a journal article and I say something like, oh, well, the odds ratio for this is 3.5 or something like that, in the actual paper, it's calling directly from one of these tables and inserting the values, so in case I change my data, it updates all the values in my text. You just subset into there like that. I think I have an example. No, I don't. I removed it for time, which is perfect because we have 5 minutes left. Okay, so you can get into here with subsetting like you can into any other object in R, because every object in R is exactly the same thing and uses the exact same operations.
Could you then export summary items into Excel or something?
Yep. Yeah, you just save that. You could, this right here would pop out in Excel as just rows and columns like an Excel sheet, very easily. Or you could save it as an R object and load it in somewhere else and it will have all those numbers saved in it. Yeah, just export. You could also send this into like a function that generates nicer looking tables. I generate all my tables in my articles actually by extracting all the values out of here and having to auto-generate tables because it saves me a ton of time. Yeah, tons of power, tons of flexibility. The rabbit hole is endless with this stuff too. I mean, you can definitely waste very large amounts of your life, as I have done, to do very clever things that didn't actually save any time. But they're damn cool. Yeah. These slides are actually an example of that. There's so much hardware going on under these particular slides that it was totally unnecessary, but I get really into it. Okay, another thing somebody asked on the spreadsheet sign up that is like, how do I fit an ANOVA? Well, the thing is an ANOVA is a specific subset of a linear model. It uses the exact same syntax and stuff. It produces just slightly different output. So I do AOV is the base ANOVA function, life expectancy by continent, data equals gapminder, and now what I see here is continent is all the values are sort of collapsed because we're only really interested in decomposing the variance between like everything and whatever variables I give it. This just says, oh, continent has some statistically significant contribution to the overall variance of the object. That's that. You can get more output by digging into that summary object if you want more ANOVA stuff. But it works like a linear model. I could access all the list output for that analysis of variance object and get way down deep into it. It's all in there. Okay? Next, R supports tons of more complex models, and it's probably, that's one of the reasons people get into R, because they want types of models that they either can't run other statistical packages or are just a huge pain to run other statistical packages. Like GLAM and Stata can run literally anything you'd ever want to do, but God forbid I actually have to use it. R makes these things relatively easy. The most commonly used other things are going to be something like GLM. GLM is generalized linear models. It has syntax identical to LM, but it adds on an argument, family equals, that lets you specify model families and the link functions for them. So for instance, if I want to run a logit model, I would say GLM, say X by Y, usually we do Y X, but whatever, I'm being fancy. Family equals binomial, because a logit is a type of binomial model, and then link equals logit. If I want to run a probit model, I'd say link equals probit, right? I could do something else. I could do like link equals log, or complementary log, I could do anything. If you want to do something like hierarchical multi-level models, I recommend the LME4 package, which is a kind of a slightly more simplified version of the LMER package. Very powerful. I use this and I do a lot of hierarchical modeling, so my recent article, I just got an article accepted 2 days ago that uses the LME4 package. Celebrating. I'm still celebrating. I'm going to buy a cake. So it adds GLM, hierarchical GLMs. Lavon, one of my favorite packages, adds structural equation models and uses this ridiculously intuitive syntax. You just write out the formulas as text. It processes the text and generates a structural equation model. Once I went from doing, it was the horrible Lizral. I went from doing Lizral and M+ models to this. I kind of wanted to cry. You're so beautiful, Lavon. What can't you do? And so now I teach Lavon in the CSS structural equation modeling class. And PLM and time series fit time series models and panel models. But there's a million other packages out there. These are just ones the most commonly used that I encounter. I like all of these packages except PLM, but PLM. Yeah, anyway, they all work with the same basic things I just showed you. Summary will generate summaries from those models. You use $ to access all of the things that they put out. Yeah. Thing to remember, R is huge. If there's some sort of additional model you want, Google it. There is a package out there to do everything. Because most statisticians, when they develop a new statistical model these days, they're releasing that as an R package. It's pretty much always out there. Okay, last slide. It's 159. Boom. Okay, some resources that you might be interested in. So the first one I link is a plug for myself, but actually I've heard people say it's fairly useful. That is my University of Washington Introductory R class. So this presentation was made of a mix of slides from that plus some additional new content. I don't actually teach any stats in that class, so all the analysis stuff was brand new. All my lecture videos are free online. They're updated every single term, that kind of thing. It's all in there. I hear it's pretty good content. There's an online textbook I recommend, R for Data Science. It introduces sort of the modern standard ways of doing data manipulation and visualization. It's a great textbook. Don't pay for a textbook in R. All the best ones are free, so you just go online and use them. They have print copies too, and they're dirt cheap. Advanced R, for when you get deeper into things, that's like how to do all the nuts and bolts. Data Camp has interactive R tutorials that are fantastic, and the intro R one is free. Just go on there and use it. I highly recommend Data Camp. All my students in my class get 6 months of free Data Camp, and they just think it's great. Swirl is sort of like Data Camp built into your own R. You install that package and it makes interactive tutorials that pop up in your R console, and you can go through all these exercises. Swirl is awesome, and also has a website associated with it. Great for practicing and learning R. Other things is there's a link to some RStudio cheat sheets on how to use some stuff. I didn't actually introduce most of the stuff in those cheat sheets on here. And then there's an article I like that is sort of a broad kind of theoretical thing called Good Enough Practices in Scientific Computing. This is just an article that was in a biological sciences journal, but it's talking about what is the basic set of computing practices and skills that every researcher should know just to sort of keep themselves out of trouble and make their research reproducible and useful to other people. And it's kind of nice. It goes over this general broad area of what are the more modern tools, but in a way that's not like every person should do these ridiculously hard to do things. It's usually simple steps, like how do I organize a project? How do I back things up? How do I document things in a way that's very easy? And as somebody who's a big reproducible research nerd, I think that's great. And with that, that is everything. We're exactly on time. Thank you so much for coming and joining me. This has been super fun. Questions?
So we have to check for the next half an hour. So if you can open it up for broad questions, and if that kind of fizzles, feel free to come up to chat with you and ask your very nitty-gritty question too.
General R stuff doesn't have to be related to this presentation. If you've got ones out there, I'm happy to field them. I love talking about this stuff. So we're going to dance for another team.
Do you have the form information we submitted where we said if we had any specific questions?
Does it have specific questions on there?
Well, like the GG plot.
I saw that, but I didn't include anything on it, and my memory isn't good enough to recall everything that was on there. So somebody asked about ggplot. My recommendation for that is actually to read R for Data Science, because it's written, so R for Data Science is written by Garrett Grohlman and Hadley Wickham. Hadley Wickham wrote ggplot, and Garrett Grohlman is one of the co-authors on all those packages. That book is written by the people who wrote the packages. It's really good. Go there. My course is based off of the R for Data Science textbook. I also do have great examples on mine. In my opinion, great examples. I made them myself. So if I go to my own website for this, what is that? This is my course website. Looks suspiciously the same as the one for this workshop. I have my second thing is on ggplot. So how do we plot with ggplot? And this gets into, we browse deep into here. I get pretty quickly into the syntax for plotting things with ggplot, which is a little bit different. ggplot is based on the idea of starting with a basic graphics object and adding layers of things to it, and so you kind of build things up from the ground up. That's a super cool, in my opinion, example of what that can look like. This is a plot with a lot of syntax that this went into that article. Like I said, I just got an article accepted on, Monday, I think. No, it's Tuesday. But anyway, this is the code that generated the final plot that's in one of the plots that's in that article. It has a lot of things going on. This is saying, okay, I want to generate this predicted probability plot. I'm going to what's called facet it. I'm going to make multiple plots in one. I'm going to have error bars. I'm going to have points. I'm going to have a whole bunch of different scales on it. This looks like gibberish, as it should to everyone. But what's cool is that's what the final plot looked like. So the plot was the probability that an individual gets arrested by the race of the person who might be arrested, the person who called the police on that person, the type of neighborhood they are in, and the type of crime that that person was involved in Seattle. So these are estimated probabilities on the left. This is the race of the person the police were called on, so a white person or a black person. This is the race of the person who reported to the police, because I have data on the actual race of everyone who called police in Seattle for 6 years. They don't usually give you that data. That, and then for nuisance crimes, serious crimes, and then I used a multivariate latent class mixture model to classify changing, disadvantaged, and stable white neighborhoods in terms of gentrification. And we have predictive probabilities for all of those. So if I want to know something like, what's the probability that if you are a black individual who a white person calls the police on in a stable white neighborhood for a nuisance crime, your predicted probability of getting arrested is hovering around 85%, 86% in Seattle. I like this plot a lot. It actually didn't take very much syntax work to generate in ggplot. Doing this in base R would have been a mess. ggplot is wonderful. If you're going to learn plotting seriously in R, just go ahead and learn the ggplot stuff rather than spending too much time on base R. Makes beautiful graphics with virtually no real heavy work done. Almost all of this is just me being anal and wanting very specific things, like color coding things specifically, putting the titles in and stuff like that. Yeah. So that's ggplot. I love it. I think it's fabulous. And it's easy to learn. Yeah. Any other things people want to know about? Yes?
Can you show any spatial examples?
Spatial examples. I have a whole lecture on spatial data analysis.
Just go into class. This is great.
My spatial data analysis lecture, let's see, working with geographical data. As it turns out, working with geographical data in R is really easy. It's pretty great. Let me see it. Taking a second to load here. This is my old style slides. I got rid of these, but they're okay. The first thing, though, is if you want to do GIS stuff in R, this book by Bivand, Applied Spatial Data Analysis of R, Bivand, Pabesma, and Gomez-Rubio, is the best thing. It's just amazing. So this is the kind of book that if you have this, you can basically replace QGIS and ArcGIS with R, as I have. I don't use QGIS and Arc anymore at all, because I do it all in R. If you like writing code more than you like clicking stuff, I do. Do it all like this. And then I go on, this particular lecture goes all the way into, imagine browse over that. This is me pulling census data and mapping. This is percentage black by census tract in King County. Pulling that, the amount of code required to do that is very small. So that's the code to generate the plot. That's the code to actually go to the US Census and download all of the data, create a new percentage black in each tract, everything. So that's downloading the data right there. And then the next one is plotting it. And then that's the plot that pops out. This stuff is so trivial to do in R, it's comedy, right? Yeah, I teach that stuff in that kind of class. I also teach some more complex stuff, but I have a bunch of restaurant data in here that's hilarious. Oh, these are from my field experiments. I do field experiments. I'm actually mostly a field experiment criminologist, but I do data stuff too. This is, for example, like doing plotted labels over locations of crime in downtown Seattle, where the labels repel each other so they're all readable and not overlapping. And you see these beautiful backgrounds like this. Those backgrounds are dynamically downloaded from, let's say Toner Light comes from not OpenStreetMap, but Stamen Maps. Stamen Maps online. And so you get these beautiful white looking things. And like that is all of the syntax necessary to generate that plot right there, right? There's like nothing involved in it. ggplot just handles mapping and geospatial data like it's nothing. So GIS, geospatial stuff, here's doing a heat map of crime density in Seattle. That stuff's all up in there. And it's, that's me downloading actual maps directly from Google Map. Really, just say source Google location Seattle at zoom level. Got a Google map, I can then plot data over it because it has the latitude and longitude built into this thing, so it knows if you plot points over it, they're in latitude and longitude, and will plot them. It hides many things, but if you get into things like if you need to come up with coordinate projections and stuff like that, that stuff's all handled very easily in R2. Yeah, so, I'm a fan. You had a question?
Where would I go to learn more about taking two large data sets that have, to merge them, that they have some column in common, maybe a one-to-many relationship, kind of like cheating around SQL?
Yeah, and actually I have a lecture on here on cheating around SQL. So, manipulating and summarizing data here. Later, this is the lecture I gave yesterday in my class. The theme is depth to spreadsheets. It's also, it's not depth to SQL, but it's how do we do SQL-style operations in R. So this is joins right here. I accidentally clicked one more too far. It's rendering this graphic, which is going to take it a minute. Please don't keep rendering. Okay. Dynamically rendered graphics are not great when you have like 300,000 points on a plot. Now I'm waiting for it to render this. But, oh, come on. You're not that slow. Okay, maybe you are. Let's just go to like, there we go. Okay. Joining merging data frames. So I'm glad you asked. How to not do things in Excel. And then this is saying like, how do we want to join a data frame from A to B? What is conceptually, what rows do we want, what columns do we want, what variables do we use to join? And then these are all the different types of join, which are SQL-style joins. Left join, right join, inner join, full join, sum join, anti-join. There's other types of joins too, but those are the main joins. Usually a left join does the job, as I tell my students. So this is how you do by matches in this. This is dplyr. So dplyr is this type of syntax I use for all my data manipulation. It's very fast, it's very intuitive. This way you could say, okay, if they have identical names, you don't even have to tell it what to do. It just knows to match on the identical variables. If you have some identical variables shared between them, but you only want to use some of them, you'd say, I want to match on var1, var2, var3. Maybe they have different names. You just say, I want to match on a variable in the data set A is named B variable in data set B. Match on those. And then depending on the type of sort of SQL style join you use, it's going to join in a different particular way. The syntax, it's pretty simple. I have examples here. The data set I use as an example is flights flying out of New York City, or the general New York City area in 2013. It's about 370,000 flights. And you want to join them between different data sets, like you might have the flight, but also the tail number of the plane. I can go get a data on the actual individual plane to find out its manufacturer. So that's like, it's a one-to-one join there. Well, actually, no, that's a many-to-one join. It's all in here. This syntax is very easy, in my opinion, even for complicated joins. You can also actually run SQL through R using like RStudio and dbplyr, database plyr, which is dplyr for SQL calls. Very easy to do. So I have people who come to me who have SQL experience and do a lot of stuff in SQL, and they find it very easy to jump into doing joins and things. And actually, using dplyr syntax in general is pretty easy for those people. You can also do all your stuff in SQL and just pipe it straight into R too. So if you're very good with SQL, you might not want to do any of that directly in R, but instead make the SQL calls separately or start calling it. R is perfectly happy to play all of that. Answer your question? Cool. Anything else? See, I like talking about this stuff. More questions? Okay. Yeah.
Can you talk a little bit about your favorite export formats or tricks for generating high resolution images that might be suitable for print publishing?
Ah, yes. So for print publishing, it depends a little bit. So I try and export things usually as vector graphics formats, like SVGs are usually pretty good. PDFs are okay. I don't like PDFs because it's a semi-proprietary format by Adobe, which is an evil, shitty company. But we don't do that. So SVGs are pretty good. But it depends. So usually what I'll do is I'll very often return some sort of raster graphic at very high resolution and have them scale it down. So if they have a competent publication staff at a journal, they'll be able to not butcher my images. If you're not in like a top flight journal, that's a 50-50 maybe, that they're not going to butcher your shit. But we'll see. I'll very often do, pings are actually pretty good because pings are a raster but lossless format. If you do them at a high DPI, it's pretty good. Actually, 300 plus DPI or something like that ping image. And you can do GG save to save GG plots and just say, I want to save it as a ping, give it DPI, and do that. The graphics that are embedded in my slides are all SVG images because I can zoom in as much as I want. It's vector. The problem with them is that sometimes if there's way too many elements on it, like that when it's trying to render it, I have that one slide on here that renders really fast on my computer, but my computer is a Goliath. So on most computers, like I realize that people flip that slide and it'll take 10 seconds to render it. It's like, I'm sorry. Yeah, depends. SVG is a great to send to them if they know what they're doing. If not, high resolution ping. If they don't know what a ping image is, I'll try a PDF. If they don't want a PDF, I'll try a really high DPI JPEG. So it's a hierarchy. Then sometimes they want TIFFs. Like, people want TIFFs. I'm like, fine, take it. I'll give a TIFF. They're high resolution at least. But you can do everything. Like, all those things are supported. You can get add-ons, you can do stuff. R is actually very happy doing all sorts of different image things. I actually make like animated GIFs in R and stuff. You can do image manipulation and stuff pretty great as long as you do it programmatically. Yeah. Everything we handle. That's my thing. So. Anything else?
Okay, well, thank you all for coming, and thanks, Chuck. This was really good. And we are considering holding more of these, so let us know if there's a second intermediate level of topics that you would like covered.
It sounds like there's an interesting, maybe a GG class.
Yeah.
Yeah.
And deployer.
dplyr and ggplot, I mean, that would be like a data manipulation one with dplyr and a ggplot one. That would essentially be more or less the lectures. My second and third lectures in the class would be basically the kind of thing I do, but I might orient them a little bit differently. Yeah, I'd be happy to do that stuff. Fun and easy.
Don't forget to sign up so we will be able to know who attends.